Hi guys, welcome to my YouTube channel Code and Canvas. In this video, we will be covering asymptotic notations, which is a measure of time and space complexity for an algorithm. So let's start without any further delay. By simple definition, asymptotic analysis is a method of describing the runtime or space complexity of an algorithm as the input size, which is usually denoted by n, grows towards infinity. And asymptotic notations are the convenient for describing worst case runtime functions, which is usually defined only on integer input sizes. So to understand these definitions, we will take example of insertion sort. Before going into the analysis of insertion sort, let me first explain how the insertion sort algorithm works. Let's say we have an array of 5 digits in descending order. To sort this array using an insertion sort, the number of steps will be like this. So first we will compare the second element with the first element. If the first element is larger than the second element, we swap them. So the array after the first iteration will become like this. Now we will move to another element, next element, which is 4, and we will compare it with the previous element, which is again greater than 4. So we will swap them. Now 4 will come here. We will again compare it with the previous element, which is also greater than 4. Then we will again swap them. So after this iteration, array will become 4, 5, 6, 3 and 2. In the next iteration, we will pick 3 and follow the same procedure. And 3 will be swapped by all 3 elements before it and will come in the beginning. In the last iteration, the array will become sorted. So this is the algorithm I have written for insertion sort. And this is the cost and the number of times each statement will get executed. Cost is some random constant I have taken. You can consider it as maybe the time in milliseconds or microseconds to run a particular statement, and times is the number of times the statement will get executed. Because this is a for loop which is running from j equal to 2 to the n, which is the size of an array, it will run n times. As all these two statements are inside the loop, which will be executed by n minus 1 time, because the last iteration of loop will not go inside the loop, so they will be executed n minus 1 times. Same for this last statement. Now for this for loop, this statement will be executed by the sum of j equal to 2 to n, because for each value of j, in the worst case, it will be run by run by the number of times the value of j is. So when j is equal to 2, it will be running 2 times. When j is equal to 2, it will be running 3 times, and so on. So it will be the sum of j equal to 2 to n. The statements that reside inside this particular loop, they will be running in a single iteration. They will be running j minus 1 time. For the value of j equal to 2, they will run single time. For j equal to 3, the comparison will be twice. For j equal to 3, the comparison will be thrice, and so on. So the sum of these statements will be number of times these two statements will run will be sum of j equal to 2 and of j minus 1. Now if we calculate the running time of the insertion sort algo, it will be the sum of running time of each statement executed. So the total time will be c1n plus c2n minus 1 plus c4n minus 1 plus c5 into sum of tj, where j is equal to 2 to n, c6 of sum of j equal to 1 to n minus 1, c7 into sum of j equal to 1 to n minus 1 plus c8 into n minus 1. Now if we consider the best case, which will be a sorted array like this, in this the statements that are inside the inner loop will not even get executed, because each integer which is already smaller than the next integer. So the inside loop will always be false, and the statements which belongs to C6 and 6C7 will never be executed. Hence our total time in the best case will be C1n plus C2n minus 1 plus C4n minus 1 plus C5n minus 1 and C8n minus 1. If we simplify it, which will look something like this, which can be expressed as a generic expression of an plus b, thus it's a linear function of n. In the worst case scenario, where array is a descending order, all the statements will be executed as shown before. So sum of j equal to 2n is something like this, n minus 1 divided by 2 minus 1, and sum of j equal to 2 up to n of j minus 1 is n minus 1 divided by 2. If we put these values into the formula shown above, then we get something like this. If I remove all these constants and represent them by a variable a and b, we get a quadratic equation of an square plus bn plus c. So if we see the equations in worst case as well as best case, we can say the time complexity in worst case is big O of n square and the best case is omega n. Big O and omega are the notations that are used to represent the worst case time and space complexity or the best case time and space complexity for an algorithm. Worst case running time gives us an upper bound on the running time of an algo for any input. It provides a guarantee that algo will not take longer than that. It is usually denoted by big O. Best case running time gives us a lower bound for any input. It tells us the minimum time our algo is going to take for any input. It is usually denoted by big omega. Similarly, we have average case time and space complexity as well, which is denoted by theta. So if we look into our insertion sort, let's say on an average, half of the elements which are present from index 1 to j minus 1 are less than the element which is present at index j, and half of them are greater. So for each iteration of insertion sort, the number of times the element present at j index will be getting compared and swapped by the elements present before it will be j by 2. So if we replace the j to j by 2 in the previous equation, our result will be same. We will still get a quadratic equation. So we can say that theta is same, almost same as worst case time complexity. Now while calculating the time or space complexity for any algorithm, we are only interested in the order of growth by which an expression is going to grow. For example, this is the actual time complexity for the insertion sort in the worst case, but we are only interested in the leading term, which is an square. This is because when n tends towards infinity, bn plus c, both the terms will be very insignificant to the value of an square. We can also remove the constants because they are also independent of the value of n. So after ignoring all the insignificant terms which are constants as well as the less significant variable terms, the time complexity for insertion sort will be big O of n square. Now let's look into all the annotations that we use in our day-to-day life. Let's start with big O notation. As we already know, it gives us an upper bound on the growth rate of an algorithm. It tells you the maximum time or space an algorithm will take. If you will look into the formal definitions of big O notation, big O of a function represents a set of all the functions where exists a positive constant c and a variable n0 such that 0 is less than equal to function of n less than equal to the constant into gn for all values of n that are greater than or equal to n0. Please note this can be a function fn can be equal to cgn. So as you can see in this graph, the function n before n0 can be below or above gn, but after a certain variable value of n0 it is always below cgn. So fn can be considered as a big O function for gn. If you take some simple examples, n square is big O of n cube, which is true because n square will always be below n cube for value greater than equal to 0. Similarly, n4 is not a big O of n cube because values of n4 are greater than n cube. Similarly, n can be treated as a big O of n cube because the value of n will always be less than n cube for all the values greater than 0. So just keep in mind, when we see this definition, it doesn't represent a particular function, it represents a set of functions. So a particular function can have many functions that can be denoted as big O of for that function. For example, n cube has many functions that can be put into the set of big O of n cube. Such examples are n square and n, this is same for all the notations. Now let me explain the omega notation first. So omega notation gives a lower bound and describes the best case scenario for the time or space complexity for any algorithm. If you look into the formal definition, omega notation represents a set of all the functions for which there exists a positive constant c and a constant n0 such that 0 is less than equal to cgn less than equal to fn for all values of n which is greater than equal to n0. So if you will look into the graph, it represents the same. As you can see, below n0, function n can be below or above the function cgn, but after n0, for all the values of n, function n is above cgn. So if you will look into simple examples, n cube is equal to omega of n square. It's true because n cube will always be greater than n square for all the values greater than 0. Similarly, n is not a omega of n square and n4 is omega of n square. Now let me explain you about theta notation. Theta notation is a towed bound notation which represents both upper as well as lower bound for an asymptotic behavior. Formal definition says theta functions represents a set of all the functions where exists a positive constant c1, c2 and n0 such that 0 is less than equal to c1 gn, less than equal to function, less than equal to c2 gn for all the values of n which are greater than equal to n0. So you can say fn can be considered as a theta function for a function gn when it can be sandwiched between two variants of gn function as represented by this graph. Here we have two variants of function gn represented by c1 gn, c2 gn, and fn after a certain value of n0 is always between these two graphs. So fn can be represented as a theta of gn. Since theta is a stronger notation than omega, because omega represents the upper bound and theta represents both the bounds, so we can say all the set that belongs to theta of gn will be a subset of set that belongs to omega of gn. Now, as we know, theta represents both the upper bound as well as the lower bound for an algorithm. There is a theorem which says for any two functions fn and gn, we have fn equal to theta of gn, means function n can be represented as a theta of function gn if and only if function of n can be represented as a big O of function gn as well as function n can be represented as omega of function gn. Because omega and big O represents upper bound and lower bound and theta represent both, so theta cannot be represented for an algorithm for which the input changes, input behavior changes, or you can say the order of growth changes based on the input. For example, let's in insertion sort, when we analyze the best case scenario, our time complexity was tending towards an a linear algorithm. But in case of worst case scenario, the time complexity was tending towards n square, a quadratic equation, right? So theta cannot be representing both the equations. So for insertion sort, theta cannot be calculated. Same for all the other algorithms where the rate of growth can change based on the input. For example, if you will take the insertion sort and you want to calculate theta for it, you have to provide some conditions on the input. For example, you can say theta for insertion sort is order of n when the array is already sorted, and theta for insertion sort is theta of n square when array is in descending order. Now let's look at other two notations as well. These are not used regularly while calculating the complexities in algorithms, but it's good to know them. So, little o notation. It's like a big O notation, but with a small difference. So it says as big O notations represents an upper bound, it represents a strict upper bound. So it says little o notation belongs to a set of functions where for any positive constant c greater than 0, there exists a constant n0 such that 0 is less than or equal to fn less than or equal to cgn for all the values of n greater than or equal to n0. Please note, in case of big O notation, fn can be equal to cgn, but in case of little o notation, fn is strictly less than the function cgn. This is the difference between little o notation and big O notations. For example, let's say fn is equal to n and gn equal to n log n. So fn can be treated as a little omega of n log n, because fn is always value of fn will always be less than the value of gn, as the order of this linear equation grows will always be less than this equation. Now let's come to our last notation, which is little omega notation. Again, it's like a omega notation, but it represents a strict lower bound. So it represents a set of all the function where for any positive constant c greater than 0, there exists a constant n0 such that 0 is less than or equal to cgn less than or equal to function. Again, please note, in case of omega notation, cgn can be equal to fn, but here cgn is strictly less than fn. So fn omega notation can grow at the same rate of the original functions, but in case of little omega notations, they are strictly faster. So let's take an example. Fn equal to n log n, gn equal to n. Now fn can be represented as a little omega notation of n, because n log n will always be greater than n. This is all for today's video. Thank you guys. Please like, share and subscribe.